Picture a scatter of data where two groups blur into each other, overlapping right where they meet. Ask a hard clustering method which group a point in that fuzzy middle belongs to, and it will bluntly say one or the other, full stop, no room for doubt. But that's not honest, is it? Real data overlaps, and sometimes the truthful answer is 70% this group, 30% that one. A Gaussian mixture model embraces that uncertainty instead of hiding it, and it does so with some beautifully simple probability. Let's unpack it. So what actually separates a mixture model from plain old k-means? Here it is side by side. Think about plain k-means for a moment. It makes hard, all-or-nothing assignments. Every point is slammed into exactly one cluster with total confidence, and the clusters it draws are always round balls of roughly equal size. Points sitting in an overlapping region get an arbitrary verdict, and any stretched or tilted shape gets carved up wrong, because round is all k-means really knows. A Gaussian mixture model makes soft, probabilistic assignments instead. Each point receives a probability of belonging to every cluster, so a point in the overlap can be honestly split, say 60-40, between two groups. And because each Gaussian carries a full covariance, the clusters can stretch, tilt, and elongate into ellipses, capturing shapes that k-means would badly mangle. So how does a GMM actually learn those overlapping bell curves? It uses a loop called expectation maximization. Follow it one turn at a time. Begin with a guess. Decide how many Gaussians you want. Then place each one somewhere with an initial center, spread, and weight. These first parameters are rough, often just random, and they will almost certainly be wrong, but that's completely fine because the loop is about to refine them. Here comes the expectation step. Holding the current Gaussians fixed, ask every data point how likely it is to have come from each one, given its position. Points near a Gaussian center earn a high probability for it, points in between get shared out, and now every point carries a soft membership spread across all the clusters. Now the maximization step. Using those soft memberships as weights, recompute each Gaussian's parameters. Its center drifts toward the points that claim it most, its covariance reshapes to match their spread and tilt, and its weight reflects how much of the data it now owns. The Gaussians shift to fit the evidence they were just handed. Then simply repeat. Re-estimate the memberships with the improved Gaussians, update the Gaussians again back and forth, and with every pass the fit gets a little better. After enough rounds the parameters stop moving, the loop has converged, and you're left with a set of Gaussians that describes the data and gives every point its soft cluster probabilities. Strip it all down, and three ideas make a mixture model special. It models the data as a blend of Gaussians. Rather than a single shape, the data is described as several overlapping bell curves added together, each with its own center, spread, and weight, so the mixture can fit surprisingly rich and layered distributions. It gives soft, probabilistic memberships. Instead of forcing each point into one bucket, it reports a probability of belonging to every cluster, which is exactly what you want when groups overlap and you'd rather know the confidence than pretend there is none. It is fit by expectation maximization and captures elliptical clusters. That expectation and maximization loop steadily tunes the Gaussians, and because each carries a full covariance, the model handles stretched, rotated, uneven groups that round-only methods like k-means simply cannot. Alright, let's lock in what matters. A Gaussian mixture model treats the data as a blend of several overlapping bell curves, each Gaussian with its own center, spread, and weight. Instead of hard assignments, it gives every point a soft probability of belonging to each Gaussian, which is genuine cluster membership with honest uncertainty. It is fit by the expectation maximization loop, and its full covariances let it capture elliptical, tilted clusters that k-means, a special hard assignment case, gets wrong. Its costs, you still choose the number of components, and it can settle into a poor local optimum depending on where you start. If this way of explaining machine learning resonates, a whole lot more is waiting for you over at standarity.com. Come explore.